Now we're starting some of the other problems that aren't quite as long from chapter 16. And so I'm using these for more of a scalar approach. The prototype rotating bicycle rack is designed to save space at a train station. The combined weight of platform BD and the bicycle is 40 pounds. So we're going to have a weight of everything here equal to 40 pounds. And is centered at 1 foot above the midline of the platform. Okay, so they're telling us, here's the platform. We go 1 foot up. So 1 foot up. And that is where G is going to be. I'm going to make G right there at the center of the pedals. The motor at A, so over here we've got a motor, causes the support beam AB to have an angular velocity, omega, n RPMs, and we can switch that over into radians per minute, 1.0472 radians per second. When the angle, and we have a 0 acceleration, so alpha AB equals 0 when theta is equal to 60. At this instant, determine the vertical components. Okay, they only want the vertical of the forces exerted on platform BD by the pins B and D. So I'm looking for BY and DY. All right. Let's look at our acceleration components are a good place to start. If we want to look at the acceleration of the center of the mass, where this is all one unit, the bike and the platform, we're going to be looking at, I'm not drawing a bike, but we've got a point G there. That is 1 foot above the base. And this is going to be 3 feet from B and 3 feet from D. And I am looking specifically for BY and DY. And I'm going to have an acceleration component. This has 0, so we've got a link here that's driving everything. We'll start to look at a free body diagram of what's going on there. I'm going to have an AY and an AX. I have a center mass for that. I have a moment that's causing it to rotate in the counterclockwise direction. And we know that our angle is 60 degrees. And I'm going to have equal and opposite when it comes to my forces. So I'll have a BY pushing down over here. They aren't asking or giving much information on this link at all, so I'm not too concerned about that. What else might I need? My acceleration components. There is no alpha here. We only have the omega. And they told me that omega RPM, and so they didn't give me an actual angular velocity, but I am going to go with the direction of the motor and the moment. So we're going to go with omega this direction. And then we would have an acceleration in the normal direction, and we would have an acceleration in the tangential direction. And we would have, if we have no rotation at B, well, we will not have a tangential component. We're only going to have a normal component, because in order to have a tangential component for G, tangential plus normal, we would have to look at an alpha crossed with an R plus R omega squared. So up here, when they tell us we have no acceleration, this term is going to go to 0. And so we're just going to have acceleration in the normal direction. And then this would also go to 0. We are not going to have any tangential acceleration components without an angular acceleration. We're only going to have normal components. So that means my acceleration of the center of mass for this unit is going to be equal to R omega squared. They gave us an omega value. What is our R going to be? Let's look at B relative to A. If we are looking for the acceleration of B, we want to find the acceleration of A plus the acceleration of B relative to A. I know that A is not moving, so that goes to 0. And if I have my alpha cross R, and I know my alpha is 0, that goes to 0. And so I'm left with my R omega. I'll draw it out the way I have been. Omega crossed with omega crossed with R of B relative to A. Okay. So the acceleration of B is going to be equal to 1.0472, and that I drew as positive K. And we're going to cross that with 1.0472 positive K and R of B relative to A. R of B relative to A is going to be 5 feet, and my X and Y components, it would be 5 sine of 30 degrees in the I direction and 5 cosine of 30 degrees in the J direction. Okay. And B relative to A is positive for both of those. So I can find my acceleration of B if I put in this R component of 5, 2.5, if we're sine of 30. We'll just put that in there. Plus 5 cosine of 30 degrees J. We're going to ultimately get our acceleration of B. That is going to be equal to, let's see, equal to 5.483 feet per second squared. And that's going to be right down the normal component towards the rotation. So it's going to be like that. And that is what's driving everything. So we're going to move as a unit, where this acceleration component is going to be all the way through, including right here at G. Acceleration normal component is going to be parallel to these links, and everything is rotating together with a normal component. So this is going to be equal to AG and any other point on this assembly. So right there, right there. And that means we are 30 degrees away from the vertical. So there we go, 30 degrees. Okay. So I'm doing a little bit of vector for those of you who want to do vector and filtering in some of the scalar. Now we're going to look at summing forces in the X and the Y direction and summing moments. And we're going to sum moments around B. Let's look at that. Set up our typical equations. Mass times acceleration in the Y direction. We can start writing things down, figuring out what we want to work with. If I look at the Y components, because they told me they didn't really care about the X components, they only wanted vertical, we would have by and a dy, which are what we're looking to find. And we're going to have a weight. Yes. Weight coming down. So minus the weight is going to be equal to the mass. And the mass of this whole thing was 40, wasn't it 40 pounds divided by 32.2. And then we want to get the Y component of that normal acceleration term. So our normal acceleration, the Y component is going to be the cosine of 30 degrees. And so 5.483, 5.483, and cosine of 30 degrees. And that was going down. So if we're using a conventional coordinate system, this is a negative Y. And so I'm going to put that out front. And let's see, what else do I know? I don't know BY or DY. I can put in my weight minus 40 and slugs, my distance, my going to be equal to, what does this all come down to? My mass, I'm going to write the mass out. 40 divided by 32.2. is going to be equal to 1.2422 slugs. And if I take 1.2422 and multiply it by 5.483 and multiply that by the cosine of 30 degrees, I get a minus 5.898. 5.898 and another 5. Okay. Then if we're bringing the 40 over to the other side, and we're going to add 40 to that negative number, we're going to get by plus dy is going to be equal to 34.10. All right. And we can solve in terms of by is going to be equal to 34.1 minus dy. All right, we have a relationship there. Now the x's aren't going to help us, but summing moments somewhere will. And I'm going to sum moments around b. I bar alpha plus m a g times distance. So by summing moments around b, I get rid of one of my unknowns. And that sets me up to be able to build an equation where I'm just going to have to deal with dy and the weight. I already know my alpha is going to be 0, so I don't have to worry about finding an I-bar, and they didn't give me enough information to really do that anyhow. My mass, my acceleration of the center of mass, and the distance. So we've got a little bit of a distance that is going to be 3 away from B in the plus 3I, my distance, and it's going to be 1 up because they said this center of gravity is 1 up from the platform. So plus 1J. That's going to be my distance right here. I already know my acceleration components. I have found that right here. And if I wanted to put it in component form or vectors, I would have the minus, let's write it all out, b minus 5.483 times the sine of 30 degrees for my I component, and I'm going to have a minus 5.483 times the cosine of 30 degrees for my J component. That means my acceleration at B, which is also my acceleration at G, it's the acceleration for the whole system, minus 2.7415 I, and minus 4.748 J. So I have this term, I have this term, I know what my mass is, and I've got to figure out the moment arms for dy and the weight. If I look at dy, I am going to some moments here at B. So dy is 6 feet away, and it's going to be a plus k. 6 dy. If I look at my weight, that line of action is 3 feet away, and it's going to be a minus k component, minus 3. And my weight was 40. So I've got those. I have no other forces that I need to worry about if I'm looking at the bicycle and summing moments at B. I just have to look at the acceleration components now. So that's going to be equal to the mass, which I already figured out here, 1.2422 slugs. And my acceleration at G is going to be the acceleration components of 0.748J. Right? And then my D component. So this is what makes this problem a little trickier. 3I plus 1J. We haven't had this problem before. Let's look at resolving this and multiplying the slugs. So we bring up the acceleration component, and we are going to end up, if we multiply this together, we're going to have this side equal to minus 3.405I minus 5.9J. So I just took the slugs and multiplied it directly. There's no cross product there. But we do have to cross our distance. This is the distance crossed with the acceleration of G. So if we build this into a matrix, that's going to be the easiest way to probably resolve this and see it. If we have I, J, K, we have 3I. So just like doing a moment in your statics, and we've got the D values here, 1 and 0. And we're going to have the acceleration component, G, on the bottom of minus 3.405 and minus 5.9 and 0. And if we work the cross product there, the i's and the j's are both going to be multiplied by 0. We're only going to have a k component, which matches up with summing moments. And we're going to end up with 3 times minus 5.9 minus a minus 3.405K, which is going to be a minus 14.295K. Okay, so let's just copy this down. dy minus 340. I didn't do anything on the left side yet. And we're going to have minus 14.295K on the right-hand side. Minus K. All right. Then we can solve for dy. dy is going to be equal to 17.6175 pounds. Right. This becomes positive, other side. And divide by 6. And then we can take this and multiply or plug it in up here. And we will find that by is going to be 16.48 pounds. Okay, and that is all that they asked for in this problem. Right, here we have a problem with a truck that is hauling a boulder on a pallet. We have a truck that has a mass of 2,000 kilograms. So that's not its weight. It is being used to lift a 400 kilogram boulder that is on a 50 kilogram pallet. Knowing that the acceleration of the rear wheel drive truck is 1 meter per second, determine the reaction at each of the front wheels and the force between the boulder and the pallet. All right, let's draw a free body diagram of the truck. So here's my truck, and I have front wheels and rear wheels. It is rear wheel drive. So we are looking at having the force of friction moving the tires. We're going to be going from the center of mass at an acceleration, AG, equal to 1 meter per second. So that's our mass acceleration component. If we're going in this direction, then our tires are going to be spinning in this direction, which means that our friction force is going to the right. We're going to have a normal force for the rear wheel. We're going to have some tension that we're pulling. We're going to have weight coming from the center of gravity. We're going to have a normal force for the front wheel. We are not going to have friction on the front wheel because it is a rear wheel drive vehicle. We have some information on distance. We know how far the tension is from the road, and we know how far the center of mass is from the road. Okay, let's start by summing a moment around the rear wheels, which I'll call R, and I'll call the front wheels F. Summation of moments around R is equal to I bar alpha plus MAG and distance. And that distance again is from R, from G to R. All right. Let's read carefully. Do we have any alpha in this problem? Nothing is rotating. The truck is not tumbling down the road. So we do not have an alpha. And that makes the I bar irrelevant. So we don't need to find that. If we look at what we do need to find in terms of statics, if we're summing moments at R, we knock out these two unknowns, and we have only the unknowns related to the front wheels and the weight and the tension. So let's build that left side of the equation first. I am going to have a negative NF multiplied by the distance between the rear wheels and the front wheels, which is 3.4 meters. W, that's going to create a positive moment. So 2,000 is kilograms. We want to change that into weight, multiply by gravity, and we're 2 meters away. The tension, if we're going from R to the line of action for the tension, we are using this 0.6 number. And the way I've drawn it, that would be a negative moment. Tension multiplied by 0.6. Now, what does that all equal? It equals this right side of the equation. I know the mass, so equals 2,000 kilograms. I was told the acceleration, so that is easy. That's supposed to be squared. There we go. And then the distance. The distance that we're looking at is the distance right here, just like summing a moment. We have this line of action for the acceleration component. And we're going to be using this distance right here to do our moment. And that should be from R to G. R to G. And so that's equal to 1 meter. This means that we have an equation with two unknowns. We do not know the tension, and we do not know what's going on with the front wheels. Let's see if we can figure out an equation that can help us with the tension. One of the things we could do is focus on the other thing that they've given us that's pulling on this tension. So if we have this boulder on a pallet, boulder, and we have a system where we've got a pulley again. And so we have two T's. And if the truck is going to the right, the pallet is going to be going up. So mass times the acceleration of gravity for the pallet and the boulder. We're going to have a weight that's going down. And so we can neglect any forces in the X direction, but we have a lot going on in the Y direction. So let's sum forces in the Y direction equals to mass times the acceleration of the center mass in the Y direction. Now, if I am looking at my acceleration component and the truck is going to the right 1 meters per second, is the boulder going up at 1 meter per second? It is not. Just like we have our distance here and 2xb, let's say, and an xa, we are going to have the acceleration of the center of mass for the boulder and the pallet going to be equal to half of what the acceleration of the truck is due to the pulley. So meters per second squared. So I know what this is. That's going to be 0.5. I think I was told the mass of everything. There's the mass of the truck, but the boulder and the pallet together are going to be 450, and they're moving as a unit together. So I'm going to have 450 kilograms multiplied by 0.5 meters per second squared. That's the right-hand side of the equation. I'm going to have a negative weight, and I'm going to have 2t going up. And that's the statics side of the equation. So 2t minus the weight, which is going to be the mass of 450 kilograms for both the boulder and the pallet, multiplied by 9.81 is going to be equal to the 450 kilograms multiplied by the acceleration of 0.5 meters per second squared. And I can get a value for t from here, 2,320 newtons. Now I can solve for NF. So bring this value, substitute in for t, and I am going to get a value for NF that is equal to 10,544 newtons. Now we do have two front wheels, and so this would be split between each wheel. So the actual answer, two front wheels, would be half of that. 10,544 divided by 2. And that would be 5,270 newtons going up for the two front wheels. I still need to find the force between the boulder and the pallet. So now we have to split this up and look at what is going on between the boulder and the pallet. So I am going to draw a free body diagram of the boulder. So I have the boulder, and we are going up. And again, that acceleration of the center of mass is going to be equal to 0.5 meters per second squared. That doesn't change. We're going to have a normal force from the pallet. I'll call that NB. And we're going to have a weight, which is going down. And that's going to be the weight of the boulder. Let some forces in the y direction equals to MAY. We're going to have a positive normal force, a negative weight. We're going to have the mass of just the boulder this time. We're going to have the same acceleration component of 0.5 meters per second squared. we can calculate the weight of the boulder. So NB minus 400 times 9.81 equals 400 times 0.5. And that normal force that is supporting the pallet has to be strong enough to support that boulder is going to be 4,124 newtons going up. Okay, so that is the truck problem. Now we're looking at the last problem for chapter 16. And there is some errors in the solution manual for a lot of these problems, really. This one is one of those. A crate of mass 80 kilograms is held in the position shown. Immediately after the man accidentally drops the right end of the crate, assuming that the box does not slip at point E, so it's pivoting around E, that would be the center. Determine the angular acceleration, so we want alpha of the crate. And it would make sense that alpha is going in this direction, which would be clockwise. The reaction at point E. So E, we're going to be looking at an EY and an EX. What would this look like if I draw the free body diagram of the crate? I am going to have put the center of mass in the middle. We're going to have a weight going down, and at the edge, we have the corner at E pushing back on the crate. And now we're going to have an I bar alpha as it rotates down. It's going to have a tangential component like that and a normal component like that. That is our free body diagram. Let's look at what we need to do to find the moment of inertia for a big rectangle. So this isn't a rod. The equation is going to be 1/12 times the mass, and we need to take into consideration both of the distances of the crate. So this problem is going to be equal to, we've got an 80 kilogram crate and A squared and B squared. I'm going to go 1.2 meters squared and 0.5 meters squared. So that's the I bar for a rectangle. Bar. It's going to be 11.2667 kilogram times meter squared. And we're finding alpha around point E, EX, and EY. Or we could say the alpha of the crate really is what's happening. Crate. First, we've got to figure out a little bit of our geometry. I'm putting the center of mass at the center of the crate, which means that I've got an X and a Y component and a value of R. So this is the way it is pivoting. So we can see that kind of circular shape. We're going to have that normal force directed at the center and the tangential perpendicular to it. If I look at this distance here, I take 0.85, which is the distance of the crate to the wall, and I subtract the 0.6. I'm going to find out this there I'm left with 0.25. So this distance is 0.25, and half of 0.5 is also 0.25. So I've got a triangle with a 45-degree angle and 0.25 meters for each of the legs, 45 degrees for each of the angles. What is this hypotenuse going to be? Because that is really my R component. That is the distance. If we're looking at tangential acceleration, R multiplied by alpha is going to give me the tangential acceleration at G. So all I have to do is the Pythagorean theorem of 0.25 squared plus 0.25 squared is going to give me C squared, where C is going to be 0.35355. And that's the hypotenuse, which is also going to be equal to my R components, the distance between G and E. I am going to sum moments at E. And that gets rid of these two unknowns. And that is going to be equal to my I bar times my alpha plus mass times the acceleration of gravity and distance. On the left-hand side of my equation, the only force I have to deal with is the weight, and that's 0.25 away. So I'm going to have 0.25 multiplied by the weight, which is going to be 80 multiplied by 9.81. And I'm really trusting my instincts. Instead of doing this a vector way, I am doing this all in a scalar approach. 11.2667 is the I bar. The alpha is what I'm looking to find. I know my mass of the crate is 80 and AG. So if I'm summing moments at E, the normal component of acceleration goes through E. So I only need to deal with the tangential component. And remember, the acceleration tangential is R alpha. So right here, I'm going to have my alpha, my R component, which is the 0.35355 number. And then I need my distance. And that is the distance if I'm summing moments at E from E to G. From E to G. That would be, I'll put that in as squared because it's the same value. This distance here. There I can solve for alpha. Alpha is the only unknown, and it would be 9.226 radians per second squared going in the clockwise direction. Now, I also need to find out what is the corner going to have to deal with in terms of the forces from the crate on the corner. That means summing forces in the x direction equals to max. My x component, I only have an ex. My mass, that's going to be 80. And now I need to divide that component of the acceleration into its X and Y direction. So if I'm going to sum forces in the X direction and I'm looking for the acceleration in the X direction, I am going to have to consider AN. And what is happening with AN? Because it would have an X component and it would probably be significant. But what we're looking at is the acceleration in the normal direction is equal to r times omega squared. And omega is equal to 0 immediately after the man drops the box. So we are instantaneous here. Otherwise, we would have to take into consideration the normal component as well. This problem has been simplified where we only need to take into consideration the acceleration due to the tangential component. So I'm looking at AX is going to be equal to the acceleration in the tangential direction with its X component only. So if we're looking at this acceleration right here, we want the X component and there's the Y component. We're going to have a 45-degree angle. And I can use the cosine of 45 to get my X component. So the acceleration in the tangential direction is r times alpha. And let's go ahead and put that in that order. I'm going to have a value of r that's equal to 0.35355. And I'm going to have a value for alpha that's 9.226. That is my tangential acceleration, but I only want to use the X component. So I'm going to do the cosine of 45 degrees. And that gives me an EX that's equal to 184.5 newtons. What's going on for our EY component? Sum forces in the Y direction equals to mass times the acceleration in the Y direction. I am going to have a negative weight. I'm going to have EY, and that's all on the left-hand side, plus EY. It's going to be equal to the mass again, and the same acceleration component of the tangential acceleration, 9.226, and this would be sine of 45 degrees because we only want the Y component. If I plug in the value for weight, we're going to have minus 80 times 9.81 plus EY, and all of that is going to be the same thing because it's got a 45-degree angle, 184.5. And if we bring this, is going to be 784, and bring that over to this side, it's going to add to it. And our EY is going to be equal to 969.3 newtons. That is our answer. And this is the radians. And again, the solution manuals aren't really a lot of help for this chapter. If you have questions, go ahead and send me an email. Okay.